Right. Can we start? Okay. So I'm refreshing our memory about basic facts of general relativity. And I have to finish this with some additional remarks on the field equation. So we had the field equation already on the board. We will have it several times again on the board, I guess. That's what it looks like. And I think I reminded you that one can motivate this equation actually fairly well. Nowadays, at the time of Einstein, the motivation was not so strong. So there's a theorem which was proven by David Lovelock in the 1960s, which says that if you want to have here on the left-hand side an expression which is formed out of the metric and doesn't contain derivatives higher than the second derivative, and if this expression satisfies the conservation law, so the covariant derivative contracted of this side should be 0, so that automatically this equation holds, then the left-hand side is uniquely determined. So the surprising thing is that you do not have to require that the left-hand side is linear in the highest derivative, and you do not have to require that it is symmetric with respect to the indices. Both things come out. And actually proving the symmetry, so the statement that the theorem works without assuming the symmetry, that's the hardest part of the proof. Lovelock did this in the second paper. So he wrote 2 papers. In the first paper he assumed symmetry, and the proof is well long enough, but it can be done in a reasonable amount of time. But if you, then in the second paper he did it without the symmetry, and then it's much, much more complicated. So if you want to have something here which is non-symmetric, and some people do want to have this, namely those people who think that there might be high spin densities in the universe somewhere. So matter which is composed out of spinning particles and the spin density doesn't average out, then they would like to have an energy momentum tensor with an antisymmetric part on the right hand side. And then you have to modify the theory if you want to retain the assumption that it is formed out of the second derivative, and if you want to have this conservation law. And the modification which you have to do, and what some people advertise, if they want to include an antisymmetric part here, is to include torsion. These are theories with torsion, more general theories in general relativity. But that's not what we are doing here. We are doing general relativity, and then you have automatically, if you now assume this field equation, you have automatically this conservation law. Well, I call it the conservation law, just to be a little bit careful. It's not a conservation law in the sense that you can integrate it over a finite region. It's a conservation law only in infinitesimally small regions. There you can integrate it in the sense that it says the change of energy inside a certain volume is equal to the flux of the energy over the boundary. That's what it can prove for infinitesimally small regions. For big regions it does not hold, and the interpretation is for big regions, the gravitational field does something to the energy. So the gravitational field doesn't have an energy momentum tensor. It cannot have an energy momentum tensor in general relativity. So we cannot have a true conservation law for the matter alone if the gravitational field is not negligible. Okay, so then I already mentioned 2 examples for the right-hand side. So we have to, when we discuss Einstein's field equation, we have to specify for what kind of matter we want to do this. We have to specify the right-hand side, not in the sense that we write down, in terms of numbers, the components of these things, but in the sense that we require the right-hand side should have a certain structure. And the easiest assumption, of course, you can make is that we have vacuum, that we have the 0 here. I already mentioned a couple of examples for this, for vacuum solutions. Then the second thing I mentioned was an electromagnetic field, where this has a structure of an electromagnetic field. And the third example we want to discuss, which is actually the most important one in view of cosmology, is a perfect fluid. So for a perfect fluid, the energy momentum tensor has the following structure. I think there's a c squared here. I look it up. I always make mistakes with the factors of c. U mu nu plus p g mu nu. I think there is no c. Let me check. Yes, that's true. So that's the energy momentum tensor for a perfect fluid. For what do we have? We have u mu is a 4 velocity. And as usual, we normalize it. So let me write it in this way. We have the convention of pulling indices with a metric that this is minus c squared. Then the mu is the energy density. And the P is a pressure. I should say the rest energy density, so if you calculate the energy density of this thing in the rest system, this means that you form, well, just as a side remark, that you form this expression. That's the energy density in the system which is co-moving with the fluid. And if you insert this, you should get mu times c squared. Let me see. This gives no c to the 4, right? Let me see. C to the 4. C squared, and the p terms drop out. Yeah, because this gives this gives a plus c to the 4, this gives a minus c squared, and these two terms cancel, so it's correct. Okay, so the geometric idea is that we have a fluid, it's flow lines, so these are the integral curves of this vector field u mu. So at each point we have a vector u mu, the 4 velocity, and the integral curves of this flow are the flow lines of the matter in the space-time. It's a space-time diagram. And the matter is characterized by a pressure P and by a density mu. And then we usually need an equation of state in order to have a determined system. An equation of the form, f of P and mu is 0. So they should be related in a certain way. And we will usually assume equations of state of the form that the density at a certain point fixes the pressure at a certain point. So there are no other tensor fields involved in this equation. Okay, so the simplest equation of state is a dust. So the simplest equation of this form I can think of is that I just write P equals 0, that I neglect the pressure, and this is what we call a dust. So this is matter where the volume elements do not exert any pressure onto each other, so they move just freely. The individual parcels of the fluid move just freely, and that's what relativists usually call a dust. In fluid dynamics, in particular in plasma dynamics, it is also called a cold fluid. A cold fluid is the same thing as a dust. Relativists usually say dust. Okay, so then we have, if you make this model, if you assume that the right-hand side is given by the energy momentum tensor of a perfect fluid, or more specifically of a dust, then we have to solve Einstein's field equation. And of course, Einstein's field equation is a differential equation for the metric G. On the right-hand side, I also have the mu, the p, and the u. So I need to know something about the right-hand side. And I said already that when we solve Einstein's field equation with a certain matter source, we usually have to solve a coupled system. Einstein's field equation coupled to equation for the matter. And the perfect fluid is an example where the equation of motion of the matter is a consequence of the conservation law. That's not for all kinds of matter the case. So, of course, if this equation has to hold, then this is a mathematical consequence. So whatever you write on the right-hand side, it should satisfy this condition, otherwise the equation cannot be solved. And so this is a restriction on the equation of motion, on the differential equation for the matter. Here for a perfect fluid, we have the particularly nice case that the equation of motion is completely determined by the conservation law. That's not the case for all examples. For instance, if you have two perfect fluids simultaneously on the same spacetime, then you cannot deduce from this equation for the complete energy momentum tensor the individual motions. You only get a conservation law for the whole thing. So in general, the conservation law doesn't give you the equation of motion. So, but in this case, it is like that. So this equation determines the equation of motion for the matter. And this is the famous Euler equation. So if you plug this expression into this equation and you play around with the expressions a little bit, you use this normalization condition, it's important, then you get the Euler equation, which says mu plus p over c squared u rho del rho u sigma is equal to minus del sigma p, and there is a factor g tau sigma g tau, no, sorry, g is the speaking index, this is wrong, rho sigma, that's the right thing, plus 1 over c squared u rho u sigma. So you see, if this here is 0, this is a 4 acceleration of the fluid, right? The covariant derivative of the velocity in the direction of the velocity. So if this is 0, then it means we have a geodesic. Then the particles are freely falling into the sea. This is the case if the gradient of the pressure is 0. In particular, if the pressure itself is 0. Then we have, this is of course non-zero. Here you want to have some kind of matter content, so this is non-zero. So we have the geodesic equation whenever the gradient of the pressure is non-zero. So in particular for dust, the fluid particles move on geodesics. Here they are dust particles, they don't feel each other, and they move just freely on the space-time. I think that's easily understood. So this is called the Euler equation, the relativistic Euler equation. Of course, Leonhard Euler was a mathematician of the 18th century. He didn't know about relativity. He didn't write this thing down. He wrote the non-relativistic version of this equation. Okay, but in general, if you have a perfect fluid with a non-vanishing pressure, in particular with a pressure whose gradient is non-zero, then the particles do not move on geodesics, and the force which makes them move away from geodesics is given by the pressure gradient. So they follow the gradient of the pressure. So what we have to solve is then have to solve coupled system of Einstein's equation and Euler equation. And there are examples. I think you know examples for perfect fluid solutions. So I think one example everybody has seen is the interior Schwarzschild solution. Schwarzschild, what we usually call the Schwarzschild solution is a vacuum solution. It is valid outside of a spherically symmetric body. Schwarzschild has found in a second paper, in a follow-up paper, an interior solution which can match to this vacuum solution. So the vacuum solution describes the region outside of a star. The interior solution is a particular model for the interior of a star. And that's what we call the interior Schwarzschild solution. As always, a perfect fluid solution has to specify an equation of state, and the equation of state is, in this case, mu equal constant. It's a constant density solution. The pressure is a non-constant. The pressure has a maximum at the center and falls off to the boundary. It becomes 0 on the boundary. So that's the interior Schwarzschild solution. And this is a solution with lambda equals 0. There's no cosmological constant. of course, you can do the whole game with lambda equal to 0 or lambda unequal to 0. And so this is one example, which I think you have seen before. Maybe you have heard about the Gödel cosmos. Maybe I will do it in this course. Maybe I will mention it in this course. It's a pathological example. It has causality violation and some rather unrealistic properties. So the Gödel cosmos is a solution with p equals 0. So it's a dust solution. And lambda unequals 0. So it has a cosmological constant. It's a rotating dust solution with a cosmological constant. And the most important solutions with this property for our course, which we will discuss in great detail, are the Friedmann solutions. And in general, you can, when what you call the generalized Friedmann solution, this is a general class of perfect fluid solutions with homogeneity and isotropy assumption. So in general, you can have a non-zero pressure. In general, you can have a non-zero cosmological constant. So they will be discussed in great detail below. So that's the reason why the perfect fluid solutions will be the most important ones for the purposes of this talk. So it's really surprising how far-reaching these perfect fluid solutions are. What kind of information you can get out of such a simple model. So when we do the Friedmann solutions, we make the simplest model of the whole universe you can imagine. We assume that it's homogeneous and isotropic, so we smooth out the matter everywhere, and we assume that the matter can be described by this simple model with a density and a pressure and nothing else. And this gives the large-scale structure of our universe in a surprisingly well way. So this is the central part of modern cosmology. Yeah? Modern cosmology is based on these solutions. And then on top of them, one discusses small perturbations. But this is the second step. The basic features, the global features, are given by these solutions. Okay, so we will come to that in detail. So this was the brief review of general relativity, and now I begin with cosmology. So the next section, maybe I should continue over there. Oops. So the next section, what was it? Introduction was number 1. This was number 2. Should be number 3, right? So we will now discuss the homogeneous and isotropic cosmology. Isotropic. Okay, I will do this in 2 steps. In the first step, I will discuss just the kinematics, the geometry of these models. So I will just discuss how does a space-time look like if it has these symmetry properties. I will not talk about the field equation in this first step. And then when we have understood this, when we have understood the kinematics of these models, then we will discuss the field equation. Okay, this will give us the Friedmann solutions. I think that's a logical way of doing it. As ever so often, history was different. So Friedmann came before the people who discussed the general geometry of these spacetimes. Friedmann already jumped into the field equations in 1922. He made a particular ansatz for the spacetime, but he didn't prove that this is the most general form of a homogeneous and isotropic universe. And actually, at this time, I think people didn't even know that this is true. The fact that the spacetime with this kind of symmetry Friedmann had considered are actually the most general solutions one could consider. This was investigated more than 10 years after Friedmann, independently by Robertson and by Walker. And for this reason, I think the proper terminology is to call these purely kinematically considered spacetimes as Robertson-Walker spacetimes. So I say Robertson-Walker spacetime if I just assume that the spacetime has a certain kind of symmetry, which I specify now. I do not talk about the field equation. And when I solve the field equation, then I say Friedmann solutions. Yeah? Some people say Friedmann, Robertson-Walker spacetimes. for what I call Friedmann solutions, or they say Friedmann-Lemaitre Robertson-Walker spacetimes, because there was this important paper by Lemaitre in between, who in particular took the initial singularity seriously and propagated the idea that our universe started with a Big Bang. So the Lemaitre paper certainly is very important, but I think this investigation on the general structures of these spaces, this was kinematically done by Robertson-Walker, and the field equations were first solved by Friedmann. Lemaitre was 5 years later. So I think that's a proper terminology. Okay, so what is a Robertson-Walker spacetime? A Robertson-Walker spacetime, I first say it in words, and then I will discuss in some detail how the mathematics in these spacetimes look like. A Robertson-Walker spacetime is a spacetime Mg, a general relativistic spacetime, which is, I say it in words first, and then I discuss the mathematics, which is spatially, not as far as space-time is concerned, but as far as the space is concerned, homogeneous and isotropic. What does this mean? We draw a picture. We assume that we have a space-time which can be sliced in a certain way into three-dimensional spaces. So M is a space-time, it's four-dimensional. We assume that we can slice it into three-dimensional spaces. And each of these three-dimensional spaces, so these are three-dimensional, three-dimensional Riemannian. Riemannian means positive definite metric. Yeah? Riemannian space. Yeah, this carries a metric of signature minus plus plus plus. Now I have these three-dimensional submanifolds, and when I say it's a Riemannian space, I mean if I pull back the metric, as the geometers say, so I look at the metric which is inherited by the submanifold from the space-time manifold, then the three-dimensional metric should be positive definite. Then I call the submanifold space-like. And of course, now I have a one-parameter family of these surfaces, so that can be labeled by some time parameter, tt1, tt2, tt3, and I will have such a space for each time. And of course, the whole thing may may change in time. It's a dynamical space-time. But at each particular time, I have a space, that's the assumption, which is homogeneous and isotropic. What does this mean? It means that if I am at this point and I look around, I see exactly the same as when I am at this point and look around. And this is homogeneity. So the points have equal rights. And isotropy means if I look into a particular direction from here and I look into a different direction from here, I see the same thing. This is what we call isotropy. And so our first goal, our first task is now to investigate how is a three-dimensional Riemannian space, what kind of structure does it carry if it has this property. So we have to determine that the first step, all three-dimensional Riemannian spaces which are homogeneous and isotropic in this sense. And then we put them together by adding the force coordinate, the time-like coordinate, and then we get a Robertson-Walker spacetime. So we have to discuss now, or we have to investigate it, to investigate the general structure or the properties. Let me just write the properties, or the properties of a three-dimensional Riemannian, means positive definite space that is homogeneous and isotropic. Well, what you do, a reasonable thing to do is to look at the curvature tensor. Well, we want to do it, as I said, in 3 dimensions, so I will now use Latin indices. Yeah? Our convention was that we use Greek indices if we are in the space-time, so if the coordinates are labeled 0, 1, 2, 3. And now we are talking about, No, I think it's okay. Now we are talking about three-dimensional submanifolds. So then for this three-dimensional submanifold, I use Latin indices. So the curvature tensor so if the space-time is homogeneous and isotropic, and in particular the properties of the curvature tensor should reflect these properties. So they shouldn't distinguish a particular direction, and they shouldn't distinguish a particular point in this three-dimensional manifold, and that's what we use now. So the curvature tensor has the following symmetries, just to remind you. Oops. I had written this already last time for a curvature tensor in the four-dimensional space-time. The same symmetries also hold, of course, for the curvature tensor. Well, maybe I should use a different symbol, but I will not because I don't know which symbol I should use. You should distinguish two things. I am on a space-time. The space-time has a curvature tensor, and this curvature tensor has components which take values 0, 1, 2, 3. So in particular, I could consider the spatial components of the space-time curvature. Yeah? But that's not what I mean. What I mean is I pull back the metric onto the submanifold. This is a three-dimensional Riemannian metric, and I calculate the curvature tensor of this metric on the submanifold. That's what I denote R in this section. Yeah? It's a curvature tensor of the submanifold, not the curvature tensor of the space-time manifold reduced to the submanifold. These are two different things. So the curvature tensor has the following symmetries, just to remind you. So it was antisymmetric in J and K. We will use these symmetries now heavily. K, L, L. Yeah, so if I interchange, this follows directly from the expression of the curvature tensor in terms of the Christoffel symbols. And then we have this symmetry. If I pull down the index, I, J, K, L, then I have also antisymmetry in the outer pair of indices, R, L, J, K, I. So this is a symmetry which makes use of the special form of the Christoffel symbols, that they are derived from a metric. So here I need the metric, here I do not need the metric. And then we have this Bianchi identity, Ri plus Ra KLJ plus LJK, cyclic, JKL, 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 yes, is 0. And the second Bianchi identity, and we will use all four actually in the following. So here I have, say, I and L, I and L, I and L. And then again, the other three are permuted cyclically. J, K, M, J, K, M, J, K, M. And this is again 0. So these are the identities we have at our disposal. And now you see, because of these antisymmetries, you can use the Riemann curvature tensor as a map which makes antisymmetric second-rank tensors into antisymmetric second-rank tensors. And we will use the properties of this map in order to find out how the curvature tensor of a homogeneous and isotropic space has to look like. So this thing, R, I, J, no, the other, I, K, J, L, with this position. This can be used as a map where from antisymmetric tensors second-rank tensors, yeah, it's a set of all, that's a shorthand notation for the set of all second-rank antisymmetric tensor fields. And what comes out is again such a thing, say omega hat, what is it, Ik is summed away JL. So it's a map from a space onto itself. And how it is done? So the omega hat, JL, is just this operator, this viewed as a linear operator applied to the omega. Yeah, you see this? Because a curvature tensor has these symmetries, this makes indeed an antisymmetric second rank tensor field into another second rank antisymmetric tensor field. And now we can discuss the eigenvalue problem of this operator. It's a linear operator from a space onto itself. So it makes sense to ask what are the eigenvalues of this operator. And because of this symmetry, this operator is a symmetric operator. So the eigenvalue problem is completely solvable. And now we make our requirement of isotropy. Isotropy means that there are no distinguished directions. This means there are no distinguished vectors at the point I'm considering, and this implies that there are also no distinguished antisymmetric second rank tensor fields because they are in one-to-one relation to the vectors. Yeah? We are in 3 dimensions just a second. So you remember how the cross product, the vector product is done. The cross product just identifies vectors with 3 components with these antisymmetric second rank tensor fields. So it's exactly the same as a 3 vector. Yeah? So it maps 3 vectors onto 3 vectors, and if I have isotropy, then all the 3 vectors have equal right. So the operator is not allowed to have a distinguished eigenvalue, because then this particular vector would be distinguished. So what's the only solution? The only solution is that it must be a multiple of the identity. Then it has the same, then the eigenvector equation is satisfied for all vectors. And then of course isotropy is preserved. There was a question?
Yes. Is there just a head missing, or is there something?
Yeah, of course, sorry. Yes. Actually, I could omit the head, but then I should omit it everywhere because it's the same set. But yeah, that's what I mean. Okay, isotropy requires that there is no distinguished eigenvector So it means that this thing which I view as a linear operator, that it must be a multiple of the identity operator. And what's the identity operator on this set of linear? So it is a factor, yeah? It's a factor times the identity operator. And the identity operator, I claim, up to a factor 2 or so, is this here, delta j, delta kj minus the antisymmetrized version. Yeah? I claim that if I apply this to an antisymmetric tensor field, then this tensor field is reproduced. I think up to a factor 2. I will. So let me write here. Note that this is really a multiple of the identity operator, delta IL, delta kj, delta ij, delta k. If I apply this to my omega, ik, what do I get? Well, the Kronecker just means that I have to there's a summation over I, right? I have to replace the I by the L. So it's omega L, and here I have to replace the k by j. And here I have to replace the I by j. And here I have to replace the k by L. And the thing is antisymmetric. So this is the same with the indices interchanged and a minus sign thrown in. So this is 2 times omega Lj. Yeah? So you see it's the identity operator up to a factor 2. So, okay, if I have written k here or k halves, that doesn't matter. That's the usual convention to write it in this way. So that's a condition that the curvature operator is a multiple of the unit operator. And that's what isotropy requires. And now we have the condition of homogeneity. Homogeneity then requires, so this can be done at any point, right? If I require isotropy at a particular point, then I come to the conclusion that this equation has to hold at this point. And now I require also homogeneity, that all points have equal rights. So then, of course, the k must be a constant. Because if it has a different value here, and as it has here, then I could distinguish the 2 points. I could say this is a point where the k is bigger. Yeah? So homogeneity now requires that k is a constant. And yeah, we call we call a Riemannian space. Yeah, one says that it is of constant curvature. That's the usual abbreviated terminology, of constant curvature. Yeah, if this equation holds with a constant k. If, well, usually one pulls the indices down, so I write it in this way, is a k, and if I pull all the indices down, then the delta becomes a g, right? Pulling an index on the metric means that I get the Kronecker, and conversely, pulling an index on the Kronecker means that I get the metric. So a GIL, GKJ, minus GIJ, GKL, with a constant k. Okay, so that's our first result. When we want to consider this situation, then these three-dimensional spaces have to be spaces of constant curvature. And but I should make a remark here. Actually, I have argued that the k must be constant with the help of homogeneity. Actually, there's a remarkable fact that in all dimensions, with the exception of dimension 2, that you can prove that the k must be constant if this equation holds. And this is the second Bianchi identity. We have used this identity, and this here. We have not yet used this here. If you use this here, and if you are assuming that you are not in 2 dimensions, we are assuming we are in 3 dimensions. 3 is different from 2, so we can use this argument. Then we can prove that k is actually a constant. So let me write this as a remark. I will not do it on the board, but it's actually a very quick calculation. So remark. Remarks the second Bianchi identity. That's a Bianchi identity with the derivatives. The second Bianchi identity implies that necessarily, yeah, what you get is this equation. That's a derivative. Well, if I write a covariant derivative or a partial derivative on the, sorry, that's a k. That's a k. On the k, let me use a different index. Maybe that's confusing, having the same index. So the derivative of the k is a scalar. For a scalar, it doesn't matter if I write covariant or partial derivatives. So that this is necessarily 0. Well, actually, it comes out in this way. This is 0, but this is a dimension. Yeah. So in any case other than n equal 2, you can conclude that k is necessarily a constant. So if you just have derived the isotropy condition, if you have derived the condition that this equation here holds, and you are not in dimension 2, then you can prove that the k must be 0. This means isotropy around any point implies homogeneity. Yeah. But in 2 dimensions it does not work, and actually in 2 dimensions this equation does hold for many manifolds where the k is not a constant. Actually in 2 dimensions this equation holds for any Riemannian manifold, and in general the k is not a constant. K is what is called the Gaussian curvature, and in general it's not a constant. Okay, so this was yeah, if you're interested, you can do this in 3 lines. Yeah, you write down the Bianchi identity and you contract the indices away so that only one index is left. Then you get this result. Okay, this was a remark. So what have we found now? So we have found that. So let me write this down. This is the first result. Homogeneous and isotropic. Riemannian manifolds. If I say space or manifolds, that's the same. Yeah, Riemannian spaces or Riemannian manifolds is the same thing. Riemannian spaces are necessarily of constant curvature. And now the question arises, how many spaces of constant curvature exist? And I will not prove this. So let me just write, one can prove a couple of things. The first thing is any two spaces of constant curvature, of course in the same dimension and with positive definite metric, that any two spaces of constant curvature are locally isometric. What does this mean? It means if I fix a point in one of these manifolds and a point in the other one, and I look only at neighborhoods, not at the global structure, just at local neighborhoods, then they are indistinguishable. Yeah, they have the same geometry. So that's what one calls locally isometric. If they were really globally the same, if they also had the same topology and they were globally one-to-one, then one would say they are globally isometric. So spaces of constant curvature, spaces of constant curvature with the same K. Are locally isometric. So they are locally the same as Riemannian spaces. Well, the proof is not very difficult, but it takes some time. And well, I remember it is given in full detail, for instance, in the old book by Eisenhardt, Riemannian Geometry, book by Eisenhardt. There you can find a full proof of this statement. So this means if we are only interested in the local structure, so we have this picture here, let me show it again. Oops. This picture where the space-time is sliced into submanifolds. And if we are just interested in local neighborhoods, so I want to say, well, if I look at a sufficiently small neighborhood of this point, then I want to have this property of homogeneity and isotropy. So this point and this point, they should have similar properties, and the isotropy should hold around any point, but maybe not necessarily if I look farther away. So then this thing is uniquely characterized by the number k. Yeah? So then there are as many spaces of constant curvature as there are numbers k, so as there are real numbers. Yeah? And well, you can imagine that if I just have one thing with k equal 2, say, and one with k equal 3, then they will differ just by a scaling factor, so they are qualitatively not very much different. So there are three qualitatively different cases. This is k positive, k0, and k negative. Yeah? These are the three qualitatively different things we have to distinguish. And one speaks then of spaces of constant positive curvature, space of constant curvature 0, and space of constant curvature smaller than 0. If you are interested in global properties, then the situation is more difficult. Of course, if you have one space with constant curvature, you can cut holes into it and you get a new one. Yeah? And there's if you allow such things, then there's an infinity which cannot be classified in any way. So to ask the question about the global structure in a reasonable way is to forbid in a certain way to cut holes into it. And one way of doing it is that you say, I'm only interested in geodesically complete spaces of constant curvature. So if I cut a hole into it, then a certain geodesic will terminate at the boundary of this hole at a finite affine parameter. So it will not be geodesically complete. If we require that all geodesics are inextendable from affine parameter minus infinity to plus infinity, then there is no longer this infinity of spaces of constant curvature. And these geodesically complete spaces of constant curvature, they are called space forms, and they have been classified for low dimensions. Yeah? So let me write this in bracket, just for those of you who are interested in mathematics, maybe a little bit more than the average physicist. Spaces of constant curvature that are geodesically complete. So in a sense, this means there are no holes into them that are geodesically complete. Holes in the sense that a geodesic can stop at the boundary of the hole. There are holes, of course, they are allowed in the sense a torus might have a hole into it. So as long as a manifold itself, it's complete. Of course, it may bend around holes or things like that. That's not forbidden. That are geodesically complete are called space forms. Raumformen in German. And that's a field which was intensively investigated in mathematics for the low dimensions, around 1900 or so. Felix Klein was one of the leading figures in this game. Okay, so that was the first statement, that they are locally isometric, which I just state without proof. So the second thing, which I will also not prove, is that they have, that they have the maximal symmetry a space can have. So what does that mean? What do we mean by a symmetry? You remember Schwarzschild spacetime. Schwarzschild spacetime, the metric coefficients, they are independent of t. So this reflects a symmetry. Yeah? We say that the vector field d by dt is a killing vector field. Yeah, that's the vector field. If I move along the flow lines of this vector field, then the metric doesn't change. I see always the same metric in my neighborhood. By the way, this name killing vector field has nothing to do with the English word kill, to kill. It is named after a German mathematician named Wilhelm Killing. So symmetries are described by killing vector fields, and the easiest way to characterize killing vector fields is in terms of coordinates. So if I can find a coordinate system that the metric is independent of a certain coordinate, let's call it t, then we call d by dt a killing vector field. That's actually not the most general definition, because it forbids the case that the killing vector field has a zero. Because if it has a zero, then it cannot be used as a basis vector field in a coordinate system. Yeah? So to cover all cases, also the situation that the killing vector field has a zero requires a mathematical structure which is called the Lie derivative. Yeah? And we say the precise mathematical definition is a vector field is a killing vector field is a Lie derivative of the metric is zero in this direction. This includes the case that the vector field has zeros. But if it has no zeros, then it can be rephrased in this coordinate way, and I think then it's easily understood. And now the question arises, how many killing vector fields can there be on a manifold? Yeah? It's easy to check that if you have two killing vector fields, then the linear combination with constant coefficients is again a killing vector field. Yeah? So they form a vector space over the real numbers. And the question is, how big can the dimension of this vector field be? And this is limited by the dimension of the space-time. So spaces of constant curvature, okay, I'm writing with my fingers. I should change the chalk. Space of constant curvature. Have maximal symmetry. It's the maximal number and this is n times n plus 1/2 of killing vector fields, of linearly independent killing vector fields. Maybe we do at least one problem on killing vector fields in the second worksheet, but I will not go too deeply into this subject. Well, let's calculate. We are in 3 dimensions. That's the case we are interested in. 3 times 4 is 12, divided by 2 is 6. Yeah, so the maximal number in 3 dimensions would be 6. So in 3 dimensions we can have a maximal number of 6 linearly independent killing vector fields. And how could they be interpreted on a space, on a 3-dimensional space slice in our manifold? Well, our idea is that the space is homogeneous and isotropic. Homogeneous means I can move in the 3 spatial directions and the space-time doesn't change. Yeah? This gives 3 killing vector fields. And isotropic means I can rotate about 3 independent axes. Gives again 3 killing vector fields. 3 plus c is 6. Yeah, that's the maximal number of symmetries. So I think it's intuitively easy to understand that we have in this case exactly the number 6 of linearly independent of symmetries, of independent symmetries. So this is the second statement which I will not prove, and which again you can find in textbooks on, well, this is also done in many books on general relativity, because it's so important for cosmology. Of course, you can also discuss this question at the level of the space-time. Yeah? If you are not in space, but in space-time, then n is 4. Let's check, what do we get for n equal 4? 4 times 5 is 20, divided by 2 is 10. So in a space-time, on a 4-dimensional space-time, we have a maximum of 10 Killing vector fields. You know an example of a space-time which has 10 Killing vector fields? All of you know one example. Minkowski space, of course. Yeah? Minkowski space. The 4 space-time translation, the 6 Lorentz boosts, the 3 Lorentz boosts, 4 plus 3 is 7, and the 3, what did I say again? The 4 translations, that's 4. Then the 3 Lorentz boosts in x direction and y direction and z direction make 7, and then the 3 spatial rotations. Yeah? Rotation around x-axis, around y-axis, around z-axis makes 10. So that's what we call the Poincaré group. Yeah? The 10-dimensional symmetry group of Minkowski space is called the Poincaré group. If you omit the translation, then it's called the Lorentz group. So Minkowski space is an example for a space-time with maximal symmetry. And actually there are 2 qualitatively different spaces in addition, locally different spaces in addition. They are called de Sitter space and anti-de Sitter space. And Minkowski is a trivial solution of the vacuum field equation without a cosmological constant, and de Sitter and anti-de Sitter are the generalizations for the case that lambda is different from 0. So if you assume that lambda is not 0, then you would assume that the trivial solution, where you have no gravitational field, is no longer Minkowski space. It's rather de Sitter, or if the cosmological constant is negative, anti-de Sitter space. Okay, but I'm moving away from the subject I was actually talking about. So what else did I want to state? I think there was a third statement. Oops, forgotten it. As maximal symmetry are called space forms. I've written this. Yeah, I think I've mentioned all these things. Okay, so now we have to. Our goal is now to look at the form these 3-dimensional spaces of constant curvature have. Unfortunately, they are not very easily visualized because they are curved in general. Yeah. There's the flat spaces, of course, a particular example, but in general they are curved. They are 3-dimensional. And if you want to imagine something which is 3-dimensional and curved, you need at least a 4th dimension. Yeah? And it's very difficult to visualize a 4th dimension. So for this reason, I will spend a certain amount of time now by discussing the 2-dimensional space forms. Yeah? Because they can be visualized. Well, not all of them in an easy way. Why not necessarily all of them in an easy way? If I have a 2-dimensional curved thing, it can curve into a 3-dimension. But in general, not every 2-dimensional Riemannian manifold can be isometrically embedded into R3. Yeah? That's not necessarily the case. There's a famous theorem by John Nash. We've heard about John Nash. There was a movie about his life. This was a mathematician who became very famous in the 1950s with this theorem, with the Nash theorem, which says that every Riemannian manifold can be embedded into a higher dimensional Euclidean space. But the dimension is not just +1 added to the dimension of the manifold, it's in general much higher. Yeah? This is a Nash embedding theorem, which was proven in '56, I think. And then John Nash became sick. He became schizophrenic, so he was not seen in public for many years. And he resurfaced in the 1990s when he actually won the Nobel Prize. Not for the Nash embedding theorem, because there is no Nobel Prize for mathematics. He won the Nobel Prize for economics, because he was then working in game theory. And well, actually, I have one personal encounter indirectly with John Nash, because once I gave a talk at a big conference, and at the same time John Nash gave a talk in another audience. And you can imagine that I didn't have many people in the audience, because everyone went to John Nash, of course. He died last year. Yeah, so he had a very it was a very, very impressive, very, very eccentric person. And as I said, there was this movie. I think it was made in the 1990s or late or early 2000s about his life. Okay, so we have the theorem that every two-dimensional Riemannian manifold can be embedded in some higher dimensional Euclidean space, but not necessarily in three-dimensional Euclidean space. So for this reason, not even the two-dimensional space forms can all be imagined, all be visualized in Euclidean 3 space, but at least some of them can. And that's the reason why I will talk about them now. So before discussing three-dimensional spaces of constant curvature, spaces of constant curvature. That's the things we are actually interested in. That's the things which are relevant for cosmology. Let's look at two-dimensional ones. So in 2 dimensions, I use capital indices. Yeah? So I now have to deal with the equation R A, B, C, D is K, G, A, C, G, B, D minus G. I have to interchange A and B. So B, C, G, A, D. Okay, with K equal constant. Yeah? I said in this case, in 2 dimensions, I really have to add as an assumption that K is a constant. It does not follow automatically. Actually, as I said already, in 2 dimensions, for every Riemannian matrix, the curvature tensor has this form with a K which depends on the space-time point. Yeah, so the Riemannian curvature tensor can be completely expressed in terms of a scalar function in 2 dimensions, which is called Gaussian curvature. Okay, let's calculate the Ricci tensor. So this implies that the Ricci tensor, this would be RCD, contraction about the first 2 indices. So what do we get? We are in 2 dimensions now. So I contract over A and B. So this gives G contraction over A and B. C and D are left. And well, what is this? This is a trace of the metric tensor in 2 dimensions. So this gives 2, right? Minus 2 GBC. What is this? This is minus K GBC, right? The metric is symmetric. What has happened to the indices? That's nonsense. CD, CD, CD. This is nonsense. I have contracted. Wait a minute, what have I done here? This is nonsense. Sorry. AC, BD. I should have a trace. In one term, I should have a trace over the metric.
Most likely just a D.
It's anti-symmetric in these 2. This is BC. No, it's anti-symmetric in BC. Sorry. I have pulled this index down. It's anti-symmetric in BC. So I have to exchange B and C. So it's B minus AB, GAD. And this looks much better. Now I contract about this. This gives a 2, right? This gives a 2. G, cannot read my handwriting. What was this? A, B, C, D, C, D. And that looks much better. Yes, this gives indeed minus G, C, D. And now the scalar curvature. The scalar curvature, this is RCC. So this gives again a 2. So it's minus 2K. Yeah? So the Ricci scalar is essentially the same as the Gaussian curvature in 2 dimensions. It just, where with my convention, this factor minus 2. Other authors have a plus 2 here. Yeah, that's the disadvantage of this index conventions or the sign conventions, that you have this minus sign here. On the other hand, if you use the other convention, if you contract over this index, then you have the minus sign in Einstein's field equation, which is also a little bit inconvenient. So that's it's a pure convention. So I have chosen this. So spaces of positive curvature have negative Ricci scalar with my convention. Yeah? That's something you have to keep in mind. Okay, let's look at them. So what can they be? So what I will do now, I will give you I will write down for you the metric for a space of constant curvature with positive k, with 0 k, and negative k. I will just write down the metric. I will give you geometric, I will argue in a geometric way that they must satisfy these properties, and then you can check for yourself that actually the curvature tensor satisfies this. So for these two-dimensional cases, it's not too difficult to calculate the curvature tensor. So let's begin with a more or less trivial case, k equals 0. So what space might satisfy this equation with k equals 0? Well, k equals 0 means curvature tensor equals 0. Curvature tensor equals 0 means flat manifold. Flat manifold means metric coefficients constant. Yeah, we can choose the metric coefficients constant. So this is, of course, the Euclidean metric. If you like, you can write them in polar coordinates. I think everybody is familiar with this. Yeah, that's the same thing in polar coordinates. So I just transform, no, the other way around. X is r times cosine phi, and y is r times sine phi. And for a certain reason, I will extract a dimensionful constant out of the r. So I will write the r in the way a times chi. So this here is a constant with a dimension, with a dimension of a length. So chi is now a dimensionless coordinate which replaces the radius coordinate. And then I have this expression. Squared, d phi squared. Yeah. And well, from this expression, it's obvious that the curvature tensor must be 0. Yeah, from this expression, you cannot read it directly, but if you like, you can also calculate it from this expression. Here you have gammas, which are non-zero, but if you calculate the curvature tensor from the gammas, you find that they are 0. So here we have, of course, r, a, b, c, d is 0. It's obvious from this expression, right? Because there the metric coefficients are constant, so the gammas are 0, and if the gammas are 0, the curvature tensor are 0. So an example for a space of constant curvature k equals 0 is a plane. And if you believe this statement, which I've just quoted without proof, then it says that we can get all spaces of constant curvature 0, that all of them are locally isometric to this. So they are either pieces of the plane, that of course they also have this, this property of the curvature tensor, or they are certain quotient manifolds of the plane. For instance, you could roll up the plane into a cylinder. Yeah? You just identify x with x plus constant, x plus a certain constant, x naught. Then you roll up the x coordinate, you get a cylinder. Has the same local geometry as the thing before. So that would be another space form with k equals 0. You could do the same thing in addition with the y coordinate, then you get a torus. Yeah? If you take a cylinder, an infinite cylinder, and now you identify y with y plus y naught, where y naught is another constant, you get a cylinder. You could do more tricky things. You could make, instead of rolling up it into a cylinder, you could identify in a crossover way, that you identify this point with this point and this point with this point. Then you get the so-called Möbius strip. Have you seen the Möbius strip? Yeah, which is this twisted belt. Yeah, I'm talking about the infinite Möbius strip. So in the other dimension, which you do not roll up, it is infinitely. And the only other thing which you can do in addition is that you do it with that you do the crossover identification with both dimensions. Then you get the so-called Klein bottle. That's a funny name. You know the story why it's called Klein bottle? It's really a funny thing. It was found by the German mathematician Felix Klein in the 1880s. And people started call it Kleinsche Fläche in German. Yeah? Klein surface. And then a textbook was written where this object occurred. And it was a German book, so it was written Kleinsche Fläche. And it was an old-fashioned typist who wrote Fläche with AE. Not with A with an umlaut, but with AE, Kleinsche Fläche. And then the book was translated into English. And the translator apparently was a bit short-sighted, so he mistook the E for an S. So Kleinsche Fläche became Kleinsche Flasche. And now everybody calls it Klein Bottle. Actually, if you see pictures of this, it has not much to do with a bottle. Yeah? It's just a surface. If you try to embed it into 3 space, then it has a self-intersection. So, and you cannot fill anything in it. It's not a bottle, definitely not. Yeah? So, and it's just a translational thing. So these are the 5 space forms. Are they 5? Let me see. The plane, the cylinder, the torus, the Möbius strip, and the Klein Bottle. They are the 5 space forms of curvature k equals 0. Yeah? The 5 geodesically complete spaces of constant curvature in 2 dimensions with k equals 0. Then k bigger than 0. I think this is also can also easily visualized. This is of course a sphere. Here the sphere is a space of constant curvature with positive k. So how do we write the sphere? I think everybody knows that the metric on the sphere of radius A, that it has the metric A square, where usually we call the polar coordinates theta and phi. For a certain reason I want to call them chi and phi in this case. So what you usually call theta, now I call chi. And then it reads this here. Yeah, you remember this? This is a metric on the 2-dimensional sphere. You are familiar with this expression, for instance, from the Schwarzschild metric, yeah, where it gives the angular part of the metric. Yeah? So this is so I think everybody has seen this, but maybe not everybody is able to prove that this is actually the metric on the 2 sphere. And because I will then translate or generalize this to the case k smaller than 0, I want to briefly indicate how you would prove this. How would you do this? The sphere is of course given in the usual way of looking at the sphere is by considering it embedded into 3-dimensional space. That denotes the coordinates in the 3-dimensional Euclidean space capital X, Y, Z. And then I have here my sphere. And I have here my sphere of radius A. So the radius is A. And now so the sphere is given by the equation x squared plus y squared plus z squared is A squared, right? That's the equation for the sphere. And if you want to arrive at this expression, what you do is you just introduce polar coordinates. Yes, spherical polar coordinates on the space. So you write x in the form, the radius is A. A is a constant here. Yeah, A is not a radius coordinate, it is the constant radius of the sphere. I only want to parameterize the surface of the sphere. So this is, how was it, cosine phi sine. Usually you write theta here, but I have called it chi now, because I want to reserve the symbol theta for something else. So y is the same thing with the sine, and z is the same thing with the cosine of chi, right? These are polar coordinates. The letters are a little bit different from what you usually use, but it's a familiar expression for the polar coordinates. If you insert this into this expression, you see that it's identically satisfied. Yeah? So by introducing these coordinates, we really parameterize this surface with phi and chi. And now the question is, what is a metric which is inherited on this surface from the Euclidean metric on the 3-dimensional space? So I write the 3-dimensional Euclidean metric on the space spanned by x, y, z, and then I pull it back to this submanifold, and then I get this expression. Let me do this little calculation. It's just 2 lines or so. And then I will do something similar for the space with negative curvature. Oops. Okay, so I write down the Euclidean metric on the 3 space, but I evaluate this metric on this submanifold where x, y, and z are restricted by this equation, which means that they can be replaced by phi and chi by way of these equations. So what is this? So maybe I should write the derivatives first. So what is dx? Dx is a cosine phi, the derivative of sine is cosine, right? D chi minus a sine phi, sine chi, d phi, okay? A is a constant radius. Then dy is the same with sine phi. The derivative of sine is plus cosine. Sine and dz. The derivative of what was it? It was cosine of chi. So I get minus a sine chi d chi. Okay? And now let's calculate this expression. Dx squared plus dy squared plus dz squared. So this squared plus this squared plus this squared. So cosine plus sine, cosine squared plus sine squared gives 1. Cosine squared plus sine squared gives 1. So I get a squared d chi squared. Yeah? This squared plus this squared plus this squared. Then this squared plus this squared gives, here again I get a 1, gives a squared sine squared chi d phi squared. And then I get the two mixed terms, d chi d phi from this here and d chi d phi from this here, but they cancel because one comes with a minus and one comes with a plus. So we are done. And yeah, that's exactly what I've written there, right? So yeah, I just pull the a squared out of the bracket and then I have the expression. So that's a way in which you can prove that the metric on the sphere is of this form. And now you see why I introduced, why I used the symbol chi, because these two expressions are very similar, right? The only difference is that I have to replace the chi squared by a sine squared of chi. And now let's do the space. Okay, so that's the space of constant curvature. So the natural topology in this case is that of a sphere. Here the chi coordinate runs from the top, from the north pole to the south pole. So it takes value from 0 to pi. Yeah? In contrast to this coordinate, which of course takes value from 0 to infinity. Yeah, we are on a plane, then it goes from 0 to infinity. This goes only from 0 to pi. So the natural topology is a sphere. And you can ask, what kind of quotients can you form from this? So from the plane, as I said, you can form 5 quotients where the manifolds are globally well behaved. Here you have only one possibility. The only possibility is to identify antipodal points. Yeah? Anybody knows what this gives if I identify antipodal points on a sphere? This is known as projective space, yeah, two-dimensional projective space. It's the same as a set of all straight lines in 3 space, yeah, because 2 antipodal points on a sphere determine a straight line through the origin, and vice versa. They are in one-to-one relation. So it's the same as a set of all straight lines through the origin in 3 dimensions. That's what calls RP2, the two-dimensional projective space. So the sphere and the two-dimensional projective space are the only 2 space forms with positive curvature in 2 dimensions. Projective space can also not be embedded into R3. Yeah? We can only embed it with a self-intersection. So it cannot be globally isometrically embedded into 3-dimensional Euclidean space. Okay, and you check now, if you don't believe it, you check that with this expression for the metric, you have indeed R, A, B, C, D. You can now, well, it's not difficult. From this expression, yeah, you calculate the Christoffel symbols. There are only, I think there are 3 which are different from 0. And you calculate the curvature tensor, and you get this is 1 over A squared, G, AC, G, B, D, minus G, A, C, G, B, D. Yeah, so the curvature, the scalar curvature K is equal to 1 over A squared. Of course, you see if A becomes bigger and bigger, if A goes to infinity, then K goes to 0. You approach the plane. Yeah? If the radius of the sphere becomes bigger and bigger, then you get you approach the plane. So, okay, this is something which I do not calculate on the board. Actually, I checked it yesterday with Mathematica just to be sure that I get all the signs right. There's a lot of opportunities to make sign mistakes, but I hope my conventions are now consistent. Okay, and now the third case, K smaller than 0. Actually, this was intuitively fairly clear that this is a space of constant curvature, that this is homogeneous and isotropic. So you ask yourself, what else can you do where you get a negative curvature? If you try to get it embedded into a 3-dimensional Euclidean space isometrically, you will see that it doesn't work. Yeah, just a question?
Just a short question. This is what you wrote there. If I see it right from the coefficient, it should be 0.
Let me see. Oh yes, you're right. I should have B, C. I should exchange B and C. G and B. That's it. Okay, thank you. Okay, yeah, what is the strategy? The strategy is to try something similar as we have done here. Yeah, something embedded by an equation of this kind, but now in a way that instead of this thing here, we get minus 1 over A squared. To change some signs in the whole calculation, and you play around and you find that you have to change 2 signs. You have to change this sign and this sign. Yeah? So the thing which I construct now, which is called hyperbolic space, cannot be isometrically embedded into 3-dimensional Euclidean space, but it can be isometrically embedded into 3-dimensional Minkowski space, where you have 1 sign changed. And that's what I do now. So this is hyperbolic space. The Russians usually say Lobachevsky space, because it was found by the first person who found this geometry was Nikolai Lobachevsky. So the Russian mathematician. Almost simultaneously it was found by Janos Bolyai. So some people also call it Lobachevsky-Bolyai space. I just call it hyperbolic space. This is certainly true. So how is this? So this is the embedded surface. So the 3 coordinates are now x, y, and well, let me call it t. So this reminds of Minkowski space, right? So that 1 dimension is different. So it is this surface, embedded surface, into 3-dimensional Minkowski space, not into Euclidean space, into Minkowski space. So this is dx squared plus dy squared minus dt squared. That's the metric of the embedding space. Okay, let's see what we get. How can we parameterize the surface to get these things here? we have used trigonometry for the sphere. So we have used identities for sine and cosine in order to parameterize x, y, and z in order to get this up there. Because now we have a different sign. What you have to do is, in one place you have to exchange the trigonometric functions by the hyperbolic trigonometric function. So you have sine by hyperbolic sine and cosine by hyperbolic cosine. Let me see if I get it correctly. So if I write x is a, we had cosine phi, and here we had sine of chi. Now I write sinh of chi. Yeah, so I replace the trig function by the hyperbolic trig function. And the same for y. This is with the sine. This is again sinh of chi. And the t is then a cos of chi, right? It's the same thing, just with a. So let's check if I really got this embedding here. So let me draw a picture. Maybe that might be helpful. So I have coordinates x, y, and t. Yeah. And I view this with a Minkowski metric, with a three-dimensional Minkowski metric. And what I want to get is the hyperboloid embedded here. That's what I want to get. This is given by this equation here. Let me see if I did it correctly. So x squared plus y squared gives a squared times sinh squared. Sinh squared minus cos squared gives minus 1. So I get minus a squared. So I think I did it correctly. Yeah? Okay, so let's calculate what the metric is. Dx squared plus dy squared. It's a Minkowski metric now, yeah? Not the Euclidean metric. So what is this? Oh, I should begin with calculating the derivatives. So dx, x is written there. It is a cosine phi cos chi d chi minus a sine phi sinh chi d phi. And divide the same thing with the cosine replaced by the sine. So this is a sine phi cos chi d chi. And the derivative of sine is plus cosine. And the t is what? Derivative of cos is sinh. Okay, and now I calculate the Minkowski metric. So the Minkowski metric pulled back to this hyperboloid. So I get this squared times this squared times this squared minus this squared. Yeah, I have a minus sign in front of dt squared. So I get here cos squared minus sinh squared, which is a 1. So I get a squared d chi squared. This squared plus this squared gives a squared sinh squared d phi squared, and that's it. Yeah, the mixed terms drop out again. And this is what we call hyperbolic space. Yeah, so this is what we call hyperbolic space. So one way of visualizing is by doing it this way, but it requires that you can visualize the Minkowski metric. Yeah? So it is not this thing viewed with our usual Euclidean eyes. Yeah? With our usual Euclidean eyes, we would say the curvature is positive. And it has here its maximum, and it goes to 0 if I go out to infinity. Yeah. So this would be, if I view this as embedded into Euclidean space, then this would be a manifold with positive curvature. But if you view it as embedded into Minkowski space, if you pull down the metric as a Minkowski metric, then it is a space with constant negative curvature. So we check that R, A, B, C, D. It's the same expression as before, but now with a minus sign. Of course, it comes from the fact that trig identities are replaced by hyperbolic trig identities. So it is this expression, but now with a minus sign. G, A, C. Let me see if I got it right this time. So I have to exchange B and C. G, A, B, G, C, C. Okay, that's it. So if you try to embed this thing isometrically into three-dimensional Euclidean space, you will see that it doesn't work, at least not globally. It does work locally. So if you are satisfied with just embedding part of it, then you can do it. And maybe you know this. The way you do it is the following. You consider the so-called tractrix. Have you heard about the tractrix? This is, well, it should become here. The tractrix is a curve, well, in German we call it Schleppkurve. Yeah? It's the Latin word for to drag, to drag. Where's the name coming from? The name is coming from if you have a boat on a river. And you start with a boat in the middle of the river, yeah, and now you drag it from the land with a rope. Then of course it will move towards the land. It will not stay in the middle of the river, and actually it will prescribe precisely this curve. That's the reason why it's called the tractrix. And if you now rotate the tractrix around this vertical axis, then you get a space of constant negative curvature. But this thing doesn't cover the whole hyperbolic space. It covers only part of it. You see, it has, from this picture, you see that it has negative curvature, because this is curved in this way, but this line here, this phi line, is curved in this way. So you have at each point, you have this curvature and this curvature. You have a saddle at each point. And this means that the Gaussian curvature is negative, because it's the product of the two main curvatures. One is positive, one is negative, so the product is negative. Yeah? So from this picture you see that it has negative curvature. There are many representations of the Lobachevsky space or hyperbolic space. Maybe you have heard about the Poincaré disks or the Poincaré half plane, or there are other things, this thing with letting the tractrix rotate, and many other ones. This is actually mathematically the nicest and the most convenient one to embed it into three-dimensional Minkowski space, but it requires geometric intuition of how the Minkowski metric looks like. Yeah? Okay, so I have 5 minutes. Let me summarize the results here. So summary is the following. Spaces of constant curvature in 2 dimensions. Again, of course, you can form quotients here. Yeah? You can form quotients, and actually the space you can form compact manifolds out of this by forming quotients, and where the space forms you can build with hyperbolic space, they have been studied in great detail, and it's fairly non-trivial actually. So spaces of constant curvature in 2 dimensions. So we have 3 cases: k bigger than 0, k equals 0, k smaller than 0. So here we have the metric GA squared d chi squared plus sine squared d phi squared, and k is 1 over a squared. So here we have g a squared d chi squared plus chi squared d phi squared, and k is of course 0, as I've written already. And for the hyperbolic case, it's this here. And here k is minus 1 over a squared. So these are the spaces of constant curvature. So locally it must have this form, and what you form globally out of it, what kind of topology you form, this is up to you. Yeah? But these would be the candidates for time slices in our Robertson-Walker universe if we had only 2 space dimensions. Now we have 3 space dimensions, and I will begin next time by writing the analogs of this in 3 dimensions. Actually, they look precisely the same. The only thing you have to do is, here we have a circle parameterized by phi. And in each of these 3 examples, you have to replace the circle parameterized by phi by a whole sphere parameterized by theta and phi. That's why I reserved the symbol theta. Yeah, I wanted to reserve it for these spheres. So in each case, I replace d phi squared by the standard metric on the 2 sphere. Then I get 3-dimensional space forms, and these are the spatial sections of Robertson-Walker universes, and we will then discuss the physics in these spaces. Okay, I'm just on time, and yeah, see you on Friday.